Extended Hückel theory. So Roald Hoffmann, we'll talk about this in a little bit. Uh, it was developed and applied by him, and he won the Nobel Prize for his application for it. He actually thought about how to do this in graduate school, but computers hadn't advanced to the point where they could handle it. But he ended up writing a program, and it helped him out a ton to do that. Physicists or other people in the solid state world often call this tight binding with overlap. Hückel theory could only be applied to what type of molecules? Yep, pi systems, ones with conjugated pi systems, and what about their geometry? Had to be planar, had to be flat. You can use this semi-empirical method. How do you spell semi? Okay. So what does semi-empirical mean again? Or what does the word empirical mean? Not in the frame we're using it. Semi-empirical means some parts are from experiment. So the word empirical means from experiment. So there's some stuff you have to use from experiment. That can be utilized for non-planar molecules. Which is advantageous over Hückel theory because in Hückel theory we could only look at planar molecules. This creates some complication in the secular determinant, which we'll see in a bit. Was developed, not initially created. We'll talk about the other guys who initially created it, but it was just developed and widely applied. By Roald Hoffmann. Who won the Nobel Prize in 1981, even before I was born. Kenichi, he was also awarded with Kenichi Fukui. Kenichi, Professor Fukui, was the first Asian Nobel Prize winner, and he got it for his explanation of frontier molecular orbital theory, so explaining how reactions happen based upon HOMOs and LUMOs, which is pretty neat. Kind of fun thing today. Today, the Nobel Prize, well, actually, kind of last night, Nobel Prize was announced in chemistry. Does anybody know what it was for? Proteins. Boring. Stuff biologists care about, not chemists. Mm-hmm. Why? They did something about protein structure, and then it was two guys from Deep AI that developed computational methods to explore protein structures. Yeah, proteins are somewhat chemical, but it's still really irritating because I want some real fundamental chemistry that's found there rather than just stuff that is bio. The worst is when it's like medical related, because then it's just like, it's not chemical at all at that point. There's many other cool things happening. Okay, so what we're going to do now is we're going to talk about how does this thing actually work, and it's cool that we've lost some of our limitations, but Of course, in order to solve most of this stuff, we have to make approximations and set limitations. So the question we're going to ask is, so how does this work? We're going to do something that pretty much all modern theoretical techniques do, barring a couple others. Oops. Shut up. There we go. We're going to assume there's a split difference between the core and the valence electrons. Do you get what I mean when I say core and valence? Okay. So the valence electrons we treat, we approximate by treating the core electrons separately from the valence. Most of chemistry occurs between which types of electrons? Yep, the valence shell. So we're really going to focus on the valence shell. We're going to say the core is left unperturbed, which may or may not be a good approximation. This also creates a problem because now we've made a difference between our electrons. And do electrons, are they actually permitted to have different labels? No, they're meant to be indistinguishable from one another. So this introduces a problem called electronic exchange. There is no classical analog to what electronic exchange is. It's just something that falls out of quantum mechanics. Okay, next time we're going to talk about some other approximations we're going to make. How does that change our secular determinant? And then we're going to be utilizing these types of ideas when it comes to talking about stuff in the solids. We can actually do extended Hückel calculations in Avogadro, and that's what we're going to do.